it looks simple, but how it boosts voltage might actually surprise you. So it starts off simple, right? So we have two sections. We have the first loop where the switch is actually closed, right? And then we have the second loop where the switch is open. Oh my gosh, sorry. Okay, and it goes through the capacitor, goes through the load, and then back to ground. Okay, we have those two cycles in the boost converter. All right, so we're going to charge the capacitor first. Okay, close the switch. We're going to charge the capacitor. All right, that's going to go through the battery. Sorry, I said capacitor. Inductor. We're going to charge the inductor. It's going to go through the switch, going to go to ground. Now there's going to be, say we have 12 volts on the battery. There's going to be 12 volts on the left side of the inductor, and then there's going to be 0 volts on the right side of the inductor. And this is because the switch is pulling it to ground, right? Pulling it to ground. Now we don't let the inductor charge fully in a boost cycle. There's problems that I can explain later, but we don't let it charge fully. We only let it charge a little bit. All right. So now let's say that the inductor is charged and that the inductor is happy. All right. Now we're going to open the switch. All right. Now here's where the magic happens. We're going to open the switch. Now all that energy from the inductor. I should mention the inductor equation, the inductor voltage equation. So the inductor voltage equation is the inductor voltage times the inductance times the change in current. All right, and I'll also write this one down: inductor voltage over inductance is change in current. What do these two equations mean? Well, they mean that if we want a big change in current, we need voltage across the inductor. All right. All right. Now, with that in mind, the inductor is now sending. We've broken its path. It's got nowhere to go. Right. It's pretty much like a dead end, and so you can't have that massive change in current because the inductor wants to keep it going and wants to preserve that flow of current. So what we're saying now is, okay, well, I've broken the switch, now go to 0 amps. So what the inductor is going to do is it's going to try and find a path, and it's going to, the voltage is going to skyrocket on the right side of the inductor, right? It's going to skyrocket to try and find a path for the electricity to flow, right? So it's going to skyrocket, and say on the other side, on the capacitor, we have 24 volts. So we've already done the cycle. There's 24 volts on the capacitor, right? Now the inductor voltage is going to skyrocket, and it's going to hit 24 volts, right? And then it needs to do past the diode threshold voltage. So it's going to go to 24.7 volts. That's how much it's going to skyrocket. And then it's going to be like, oh, now we have a path the diode is going to conduct, and now we can go through. All right, now we can go through. The funny thing about this is that now look at the inductor. Look at the voltage. It's negative now. So it's got like negative, what is that? Is that 12.3? Gosh, I don't have a calculator. Okay, sorry, it's embarrassing. Maybe it's 12.3. You know what I mean? Volts. The inductor is negative now. And if the voltage of the inductor is negative, well, look what that does to, well, you can't have negative inductance. So the change in current is negative, right? And the change in inductor voltage is negative. So now that current change is going to ramp down, it's going to decrease, and the magnetic field around the inductor is going to start collapsing, right? It's going to start shrinking. And that is how the boost converter actually boosts the current. It says, well, I've got nowhere to go, right? You want to change my current instantly, right? In 0 time, you want me to go to 0 amps. I can't do that, right? So what it's going to do is it's going to raise its voltage, right? Because if you want to have a really fast change, you need really high voltage. And so if you want to go to 0 like that, like we do, we open that switch and we allow no path to go, right? Zero amps, right? Well, then it requires an infinite amount of voltage, which can't happen physically. So voltage will just spike until it finds a path, and then once it crosses that diode and goes through the load, then it's happy, right? And then the magnetic field starts to collapse until we close the switch again, we charge the inductor, and the cycle repeats and repeats and repeats. All right, that is the fundamentals of how it works. The inductor actually reverses polarity and then flips back and forward. And that's actually how it conserves energy, to be honest. The average inductor voltage turns out to be 0, which is great. So now we'll go through the design equations on how you can actually design a boost converter. I don't want it to be too long, but I just wanted to give you the fundamentals of it. Here is the diagram that I followed. It's just on a data sheet for the gate driver. But the first equation is the voltage equation. This is super important. It's what we're talking about, right? Off and on time. It's going to let you know what you can get out of your boost converter in terms of voltage. You want to design, look, there's not many components to the boost converter. You got your inductor, you got your MOSFET, diode, capacitor, load. Your capacitor is going to control your voltage ripple, and your inductor is also going to control your current ripple, right? So you got to design around current limits. All right, so you have your inductor current. Mine's 32 amps. I think so. I'm fine, well within limits. What's your design current out? You can put it into this equation and you can find that out. Again, pick a suitable inductor. So once you've got your current, or if you already have an inductor, right? This is the minimum. If you already have an inductor and you want to, it's this equation down here. Sorry, equation 4. If you already have an inductor and you want to see the current ripple, just throw it into this equation, right? And it will tell you, okay? Now, if you want to buy an inductor that has a 20% ripple of the inductor current, then follow this equation here. Switching frequency, duty cycle, right? Follow this equation. And again, equation 5 is for the capacitor. So again, if you have a capacitor, probably follow the first equation, and that will tell you the voltage ripple. Again, you want something really small. You don't want too high. And then like 20% of your voltage out, All right, and then you have peak current, which is important. So you have to design the MOSFET around the peak current, and the diode, and all that sort of stuff, because they will all see the peak current. And then once you find the peak current, go a little bit above that too, right? Because you might get spikes, ringing, and that can shoot current pretty high. And this one here, so as I said, the current is, so equation 7 is pretty important because I dealt with it firsthand. You can't drive a gate of the MOSFET with a microcontroller. You just can't do it. The pins on there can't sync and source the current you need. This equation tells you that when you increase the change in voltage, so when we're switching on and off really fast, the current will increase. Okay, so when I was doing it, I was switching at 100 kilohertz and I was trying to drive this MOSFET and I was trying to source and sync 100 milliamps. Killed the board instantly. Killed the pin instantly, actually. The board was actually still working. So get a gate driver, which is the moral of the story. Also, I want to point out, you know, you always see schematics like this. It's really weird because in uni, like I just always was under the assumption that you have like just a microcontroller pin, just a little 5-volt controlling the MOSFET. No, you need a whole gate driver because you need to source and sync current because it's high frequency. Sure, you can run an LED or a light load off it. They recommend, so the pins can source and sync about 20 milliamps. They recommend 8. So you can run like small projects on it, like LEDs, but as soon as you get to high frequency switching, that's where stuff goes wrong. So I want to show you the actual boost converter I designed now. So this is it. So that's from one angle. See, but from the diagram, our gate driver is right here. I had to use a adapter because it's a surface mount device. But coming in from the positive side, V source is here. So we come in down the positive rail, and then we're going to be met with the inductor. So this is connected to here, okay? And then the negative is, you can't see it, but it's right behind the diode. So it's going to go through the inductor, and then we're going to have the diode and the MOSFET. So it does go to the it's the drain. It goes to the drain right here. So so that's the drain and MOSFET, and then we have the diode that comes up through here, and then we have the inductor. So they're all there at that that intersection. All right. So then the diode comes up. And then it connects to the capacitors, right, which then connect to ground. And then on the same rail, you can't see it, but behind here is the LED with the little resistor that's also going to ground. So there, after the diode, that parallels and that goes V out, which is our load. All right, again, very hard to see. And then of course, you see these resistors here for the gate driver. They're going to control your on and off time. I just put 2 10 ohms, but they're here and here, and they go into the gate, which is the first pin, right? I hope you can see this. And then for the ground, you can see pins 4 and 5. They're these white cables here, and then I've just looped them straight to ground. I could have put the ground on this, but I would have had to do double the work. All right, and then we got the PWM coming from the boost control, coming from the board. That goes into pin 9, and then this is the ground for the board that comes off the board. And this one here, VDD. All right, so VDD was just the V in. So as you can see, VDD is 4.5 to 18 volt. So I was just using the source voltage because I didn't exceed it. So I just pulled it off that rail there. And then, yeah, you can see it goes straight into pin 1, and then it's got that capacitor there. And this is what's going to supply power to the gate driver. And yeah, so this is the board that I created. It actually works. I'll show you the video of it working. There it is. Look at that. 9.3 volts. 6 in. It's done. Okay, excuse the messy desk, but here it is with 5 volts. So I'm gonna test it with a motor, just with 5 volts. All right, now we're gonna try it. Now it's connected to the boost converter. We're going to put the positive and negative on here. Again, that's 5 volt. I think we're just listening for the sound difference. Yep, I'm pretty sure I just blew something up. Oh, something's smoking. It's a resistor or something. Can you see that? Okay. Okay, so when we put on the power supply, the motor did like a peak of 300 milliamp. So the components on this circuit should hold 300 milliamp. So I'm not expecting anything to like explode or anything. So we're gonna try it one more time. I've removed the resistor. If the motor doesn't spin, I'll be very confused, to be honest. Oh yeah, oh, she's going. Can you hear that? Wow, that is significantly louder. I'd love to measure the voltage across it. Holy crap, hold on. Are we gonna get a voltmeter? Actually, we're just gonna use the oscilloscope. All right, she's hooked up. She's got 0 volts. We're gonna hook up the black now. See what we get. Oh, wow. All right, wow, it's really, really noisy. If we go to the cursor. It's like 13, we're getting like 13 volts. That's crazy, from like 5. All right, she's off. So what that tells us is we have like a really light load. Okay, so we finished up the test. That was on 10% duty cycle. We could have gone further and tried to explode, but the motor needs to be under a sort of load. So when a motor free spins like that, it's under no load. And what we know about a boost converter that has no load is that the voltage goes up a bit further than the equation predicts. So if we actually loaded that down of 5 volts, according to the equation, we should have got about 5.5 volts with a 10% duty cycle. Now, the 3 problems that we covered was, again, how to not blow gate drives and how to calculate peak current so you don't blow MOSFETs and all that sort of stuff. But then the third one I didn't really mention, but that was, so with these boards, it's got a 6-pin. You got a 6-pin adapter there, and I just sort of slotted into the perf board, thinking that it was pretty tight to go in, so all pins are contacted. And I could have actually wrapped up this project like 5 hours earlier, but because one pin wasn't, because I didn't solder it. As soon as you solder it, it's really hard to get 6 pins off. So anyway, I left it unsoldered in case it was the wrong orientation, because it doesn't actually say it on the pin. I had to go off a line. I've never seen it before. It's like a line that denotes the first pin number. So where was I going with that? So yeah, I put it in and one of the pins wasn't connected. It made the boost converter seem like it wasn't working. And so what happened was I was measuring output voltage, and I was off 5 volts, I was getting 4.7. So that was like the threshold. That was like I don't know, that was because I'm using a Schottky diode, so it might have a lower threshold, but that was like diode taking up the voltage there. That's what it looked like. So it wasn't actually working, and it was because of that pin that wasn't connected. It was the out low that wasn't connected. And so I had to take this off and then, you know, test it separately, which is why I went through so many boards to only realize that it wasn't soldered on properly. So calculate peak inductance, solder your board correctly and trust the process, and use a gate driver. And that's how you will be able to build a really good boost converter really fast. There's plenty of ways you can improve this design, by the way. Like, you can, one, use a PCB, two, start closing the loops. I mean, there's so many open loops here, right? Like, look at all these long ass wires that create parasitic capacitance, losses. Like, you saw that oscilloscope, it was just so noisy. It could be because of the motor, but I've pushed this motor so hard it gets abused really bad. But yeah, it might just be noisy. Like, look how big those diode legs are. You know, just stuff like that. Apparently perf board isn't the best for, they're good for prototyping, but not good for final design. But at least we got the final proof down pat. So we're good. And until the next video, I really want to build a 3-phase inverter or a single-phase inverter to build like a induction heater or a 3-phase motor controller. But until next time, I'll see you next time. Thanks for watching.